Hey everyone, so Owen here. In this video we are going to talk about permutation. So basically if you are permutating something, you are arranging something, so you have different arrangement, and yeah, arrangement matters here. Okay, so say you have three different colored pigeons. How many ways to arrange them into three pigeonholes in a linear fashion, right? So in a straight line. So if you are listing, you can see that there are 6 ways to arrange them. Another way of doing that is that you can ask yourself how many pigeons are allowed to enter the first pigeonhole. 1 out of 3 pigeons can enter the first one. So you put 3 in the first hole, and then you ask yourself again how many are allowed to enter the second one. So 1 out of 2 pigeons are allowed to enter the second hole. So you put 2 in the second hole, and then the remaining one directly goes to the last hole. So the last hole is 1. Hence you have 3, 2, 1, then you multiply them together. This gives you 6. Essentially you can also use the formula, which is 3p3, and that still gives you 6. But I personally prefer to use the pigeonhole method because it is much straightforward and simpler to understand what you are doing, right? Okay, so now let's say you have 5 cards, right? Ace, Joker, Jack, Queen, King, and you have 3 boxes. Each boxes can only place 1 card, right? So how many ways can you arrange them, right? Again, the boxes are in a linear fashion. So you can list them manually again, right? So this gives you 60 different arrangement. However, you can use pigeonhole method to do. Either one of the 5 cards can enter the first box. This gives you a remaining of 4 cards. Then you place either one of them into the second box, give you 3 cards, and either one of them can go to the third box, right? So you have 5 times 4 times 3 in the end. This gives you 60 arrangement. Okay, then you can use permutation, which is 5p3, and this gives you 60 arrangement as well. So now you can compare, right? You can compare the permutation formula and the pigeonhole method. So you can see that by expanding the permutation formula and then you remove the denominator by cancelling out the similar number at the denominator and numerator, you can see that at the end it gives you the same situation as the pigeonhole method. And it is also important to note that if you have n objects and you are arranging all of them, the number of different permutation or the number of different arrangement is n factorial. So you can show this by using the pigeonhole method as well. So you have 5 hole and 5 pigeons. So all 5 pigeons can enter the first hole. After that, 4 pigeons are left. All 4 can enter the second hole. After that, 3 are left. All 3 can enter the third hole. 2 are left. All 2 can enter the fourth, and the remaining one go to the fifth hole. So 5 times 4 times 3 times 2 times 1 give you 5 factorial or 120. Okay, next, let's say you have Alice, Bob, Charlie, and David, ABCD, right? And you want them to sit in a circle. How many ways to do that? Okay, to do this, you could list them. So the easier way to list is that you list them in a straight line first, and then you loop them all in the same direction. This will give you a combination right here. And then you can see that 4 of each loops are the same, just that the starting point is different. So you can cancel them out, leaving 1 of each type. This gives you 6 different loops combinations. Okay, so by formula, it is n factorial over n. Okay, so then you expand them and then you cancel it out, hence n minus 1 factorial. Okay, so this only works when no other constraints is added, I assume, right? Okay, let's look at the 2 example below. So the first one, how many odd numbers greater than 40,000 can be formed using the number 2 to 6 if each digit is used only once in each number. Here what I will do is I will break down all the available cases. I find the number of arrangement of each cases and then I add them all up. So your constraints are greater than 40,000, odd numbered, and you have 5 spots, 5 digit number, right? So a 5-digit number greater than 40,000, the first digit should be either 4, 5, or 6. This gives you 3 cases. So while dealing with constraints, you go from one constraint to another before going to the more general part. Okay, let's see case 1. We have 4 something 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 something, right? Okay, for the odd number constraint, the rightmost digit, you need an odd number. You can only place 3 and 5. So this gives you 2 types of number to place at the very last spot, right? So you write 2 there. Okay, this left you with 3 more numbers, and these 3 numbers can be anywhere. So you permutate them freely as usual. So you put 3, 2, 1, and then you multiply them all up. This gives you 12 arrangement. Okay, case 2, we have 5 something 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 something. Okay, for odd number, only 3 can go to the last spot, right? So only one type of number can be there. So there is 1. Okay, then you can fill up the rest as usual. So one of the 3 numbers can go to the first, one of the 2 numbers can go to the second, and the remaining one goes to the third. So you multiply them all up. 3 times 2 times 1 times 1 give you 6 different arrangement. Okay, you could work out the last case yourself, which is 6 something 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 something. It should be the same as case 1, giving you 12 cases. And then you add them all up, 12 plus 6 plus 12. This gives you 30 different arrangement. Okay, second example question. 6 women and 3 men are standing in the line. How many arrangements are possible if any individual can stand in any position? Okay, this is quite straightforward, no constraint. So 9 factorial lah. Second part, in how many arrangements will all 3 men be standing next to each other? So we need all 3 men together. Okay, so remember we are dealing with constraints first. So we draw 9 lines here. Then we circle 3 of them, indicating those are the men. They need to stand together, right? Okay, so we first arrange the men, right? It's easy, right? So 3 times 2 times 1, this gives you 3 factorial, which is 6. Then we look the 3 men as a whole, right? As one identity. So how many identities in total we have to arrange now? So we have 7 identities we need to arrange now. This gives us 7 factorial. In the end, we multiply them together. 7 factorial times 3 factorial, which is 30,240, right? And lastly, in how many arrangements will no 2 men standing next to each other? So this is a bit tricky. You can't take the whole minus all men together, because there will be cases where 2 men are together and 1 is not, right? So this does not fulfill our constraint. Okay, so to make our life easier, we first arrange the women first. So 6 factorial, right? Then we can see the number of gaps between women, right? So how many gaps are there? There are 7 gaps if you count properly from start to the end, right? Okay, so 7 gaps and 3 men. Ask yourself, how many gaps can the first man go, right? The first man can go to one of the 7 gaps. So 7. Okay, the second man can go one of the 6, right? Because one has been taken by the first man. So the second man can take any 6 gaps left. The remaining man can take either one of the 5 gaps left. So 7 times 6 times 5. Hence, altogether, there are 6 factorial times 7 times 6 times 5 different cases, right? Press the calculator yourself if you want the final answer, but I'm just showing you how to work out the process, right? Okay, so when should you multiply and when should you add? What I do is normally within one case, you will always multiply it, right? Let's say you are working with a case like case 1 earlier. So you always multiply within that case. For addition, when you have 2 separate cases and you want to find the total arrangement of the 2 cases, then you add them, right? Yeah, that's it. See you in the next video where I talk about combination.